one. Actually, let's remove it. So this is the threshold, sub-threshold current. Basically, when the gate voltage is smaller than the threshold, then the drain current exponentially depends on the gate voltage. So that's the only difference we make here for this cutoff. Now we call it sub-threshold. Okay, so why does this matter? This sub-threshold current is very important in determining your, for example, your device's battery lifetime. Why is that? So here, let's look at the definitions of the transistor on-state current, off-state current. So here, if the power supply of your chip is VDD, that means that is a logic 1 level of your digital circuits. You have a power supply voltage, VDD. The on-state current, I-on, of the transistor is defined as the drain current when the gate voltage equals to the drain voltage equals to VDD. So both drain and gate voltage are the maximized to VDD, the largest voltage on the chip. So in this IDVG curve, of course, this is log scale. Log scale, you have seen this before. So if your VDD here, for example, 0.9 volts, and here, if the drain voltage is also 0.9 volts, you will get a maximum current from the transistor. And in this example, it's 1800 microamp per micrometer. So this is normalized to the W, the width of the transistor. That means if your transistor is 1 micrometer wide, this is normalized to the W. It's W over L, that's W. That's geometry. So if your transistor is 1 micrometer wide, you are going to get the maximum current, 1800 microamp. Then what is off current? Off current is defined as the gate voltage equals to 0 here, but the drain voltage equals to VDD. So you still have the largest drain voltage, but the gate voltage is 0. So in this case, you will get this exponential decay current to 0.84 microamp if the W is 1 micrometer wide. So you see here we have like more than 2000 on-off ratio between the on-state and off-state current of the transistor. But the transistor is not completely off. You still have this a little bit current. So here this table shows the technology trend for different technology nodes introduced at different year. So the L of the transistor is different, and the power supply VDD will also decrease. The on-state and off-state current density is given here. So this is the technology trend. And here we care about the on-state current and off-state currents. If later when we talk about the circuits, you will see that the on-state current will determine your circuit operation speed. The off-state current will determine your leakage power, standby power. So this off-state current, here we introduce this sub-threshold current, is very important. It can explain why, for example, your smartphone here, if you are doing nothing, okay, it's in the standby sleep mode, still your battery is draining over time. Why is that? you are doing nothing, okay? But your VDD is there because you don't turn off your cell phone, right? You are still on. Then that means that VDD is there. The drain voltage, this VDD is applied to your transistor. Even you are doing nothing, it will translate your gate voltage is 0. But still you have the off current. That off current is coming from your drain, which is power supply, which means there will be a standby leakage power, which is this I off times VDD. Right? You know, power is current times voltage. So where is this current coming from? It's coming from your power supply through the transistor. Even the transistor is off, means doing nothing. So that's why your phone is still consuming power, even you are doing nothing. So this off-state current is the reason. Any questions? Okay, so let's take a closer look at this substrate slope. So we do see this straight line here in the log scale. Okay, you can take log 10 here, the base 10. So in this log scale, you have this straight line, which is due to this equation here. Anyway, so it's a exponential function. So if you take the log, then it will become linear relationship. That means a straight line here. So the slope here, the slope here is called the substrate slope, S. And it's represented as the 1 over the slope. Actually, S is 1 over the slope. This S factor is 1 over the slope. So that's why it's log ID, and then divided by VG, and then 1 over that. So actually it has two components to determine this S factor. One is because the phi S respect to the drain current. So this is the surface, the drain current. Drain current depends on the surface potential because of the exponential function of the barrier, let's say the Boltzmann distribution of the electron. So that will give you the second term. It's due to the distribution of the electron with respect to the energy level. That will give you this kT over Q, thermal energy. And here, because we take the log with base 10, you know the exponential function is the base of E, natural log. So here we need to convert the natural log E with the base 10. So if you do that, you will have natural log 10, which is about 0.3, this number. And this kT over Q, you know, in the room temperature, is 26 millivolts. So if you do these two together, this will give you roughly 60 millivolts. And then you have another factor, which is this 40 factor. This is the voltage you apply to the gate. How much of that can affect the phi S, the surface potential? It's 1 plus CDM over COX. So what is the CDM? CDM is the silicon capacitance of the depletion region. This is the depleted silicon cap. This COX is the gate oxide. So it's due to this coupling. So I'll go to this in the next slide. But the basic idea here is that you will see this S factor is always larger or equal to 6 millivolts per decade. So decade means what? Means one order. One order of magnitude. And S in this voltage. Or in other words, this S factor tells you the voltage you need to reduce for reducing the current by 1 decade. So you see here this decade, one order of magnitude. For example, it's from, let's say, 10 nanoamp to 1 nanoamp. If you reduce the current by 10 times, you need to reduce the voltage by this S factor. And this S factor is always larger or equal to 6 millivolts per decade. So that means this S is always larger than 6 millivolts. The best you can do is 60 millivolts. So this is a hard limit. This 6 millivolts is due to the physics, because these are constants, like the kT over Q, and then the natural, which is constant values. Or in other words, this will set a minimum threshold voltage of the transistor. So later when we talk about the more advanced topic later, you will see that the threshold voltage cannot reduce. So typically today's transistor, even for today's like 7 nanometer TSMC or 10 nanometer Intel transistors, the threshold voltage is still like 0.3 volts or 0.4 volts, 300 millivolts or 400 millivolts. You cannot reduce further. Why is that? Because of this S. Okay. You want to keep on-off ratio of your transistor. You want here, the current here, and current here will be orders of magnitude difference. Because one is on state, one is off state. You need to make this on-off ratio large. Right? If you make the on-off ratio, let's say the on-off ratio, here let's say this I threshold. If you make I threshold over I off, let's say 5 orders, then this threshold voltage will be larger or equal to this 5 times this S will be, let's say, will be the 5 times S, and the S is larger or smaller, larger or equal to 60 millivolts. So that means this will be larger or smaller. Larger or equal to 300 millivolts, 0.3 volts. Because you want to keep an on-off ratio large, then you need to maintain the threshold voltage above this next 300 millivolts. So any questions? So you want on and off, right? You remember this MOSFET conceptually is a switch, right? You want on and off, but unfortunately this off is not completely off, but still you want as off as possible. That means you need to have this large ratio between on and off. If you want to keep that large ratio, then your threshold voltage needs to be designed larger than that, 300 millivolts at least. Any questions? So we can take a further look why this is larger or equal to 60 millivolts. Because this factor in front of this 6 millivolts is 1 plus something. This is positive, okay? So it's always 1 point something. So this 1 point something, this something comes from here, actually. So if you look at the gate voltage, this is like MOS structure. You apply gate voltage to bend down the band here, and this is the surface of the silicon. So the voltage you apply here, only part of the voltage will show up in the phi S. So here we care about the change of the gate voltage and the change of the phi S. So this is like a voltage divider, right? You apply, because here there are 2 caps here. One is this COS, one is this C silicon. Silicon surface is also a cap due to the depletion charge. So those are 2 caps. It's a voltage divider. So the voltage divider, and then you see those two cap, and then you consider the thickness of the oxide, and then the WDM, the depletion width of the fixed charge or the dopants in the silicon. So then the capacitance, actually is determined by the thickness and also the epsilon, the dielectric constant. And then for the silicon and silicon dioxide, there is a ratio because silicon oxide is 4 and the silicon is 12. So there is a 3 ratio. So here we times effectively the oxide is 3 times thicker, effectively. So that's why you have this factor of the M, this body factor, is the thickness ratio here. It's a voltage divider. So because the gate voltage, you have a total thickness 3x, you have 3qx plus WDM, that's the total thickness here. And then part of the voltage drop on the phi s. Which part? This part. It's just a voltage divider concept. So total distance is WDM plus 3qx. That is the total voltage you apply here. Because the voltage drop on the oxide, the voltage drop on the silicon, that is the gate voltage you apply. But how much show up in the surface potential, which is only silicon part? That is only this WDM, only this part. So it's a voltage divider. So that's why you have this body factor, which is this one, which is the same as this one. So a few more words. This is a band diagram we have seen before. Ideally for the MOSFET, it's a gate-controlled device. You only want the gate voltage to bend down the band here. You don't want the drain voltage to change the barrier height here. So this is a perfect transistor. If you can do this, then your drain current will saturate, will be flat after you enter the saturation region. But in reality, it's not like this. In reality, this drain voltage will still lower this barrier a little bit. So if you have that, then in the IDVG curve, this is low, this is perfect case. This is perfect case. If this is perfect case, if you look at the IDVG curve in the log scale with different VDS, then you will not see too much difference in the subthreshold current here. But if the MOSFET here, the barrier to the source is affected by the drain voltage, like this case, you apply drain voltage, this barrier height is decreased, that means you have more electrons jump over. That means your off current will increase. So you see this IDVG curve. So then when the drain voltage is large, like 1 volt, then the drain current will increase. So this is not perfect. That means the MOSFET lost the gate control, becomes a drain control, which is not good. Any questions before we end?